This is a guide for exam 3. Now, exam 3, if we go to the syllabus, we see that exam 3 is covering O through U. So let's look at these chapters. Let's start with O. Polarization. Okay, this is your basic setup. That light is a transverse wave. So you have the E cross the B will be in this direction. You can think of it as E, B, and then the pointing vector pointing this way. That's a good thing to remember, the speed of light. And this is a nice relationship to remember also. These are basic. This you could skip. This is more electricity and magnetism, and I included it so we had all the steps, but you'll be tested on this in other courses. So we skip all this. Skip all this. Dimension analysis is important. It's not a bad thing to go through just in general to understand how to do such a dimensional analysis problem. So that's something you might look at. But then we can skip, we can skip this. It's more of electricity and magnetism stuff. You'll do that. And I guess the main thing here for the irradiance is to know that you want to take 1/2 of the amplitude squared, or the modulus squared. So I wouldn't remember. No, I wouldn't worry about this. You can skip over this. This is a nice trick, though, by the way, to figure out this little integral. So you might at least look at that integral to sine squared. And yeah, it's nice to know this integration shows up in a lot of places. So it's just nice to know this little trick here. But for the irradiance, we're going to go with mainly taking the 1/2 amplitude squared, modulus squared, like we did earlier. Now in here, I think this is important to know this, the definition. When you take the modulus squared, this is what you're doing. The z star, you definitely wanted to know that. And here I'm thinking, okay, so you would be given these, and you might be asked to do something with these, and the Brewster one is fairly short. So you should look through the Brewster, since it doesn't take that long to get the conclusion. So here it does look like, yeah, I probably couldn't put all of this on the exam because it's too long, but I think you should study this because the techniques used here are good, and I could come up with some kind of partial problem, where you do part of a problem. So that's good. The Brewster's good. I would study Brewster, and there is Brewster. And there's a nice diagram to help understand Brewster. Say this is good to go over. That's good to go over too. And here's another way of getting Brewster. See, that's very nice. Maybe too short for an exam, but not for maybe like a multiple choice or something. So this is good. This is good. The kaleidoscope's good also. Here is your formula, where this is how many things you see. One of the things is actually the object, and then there are these images. So you want to know your way around here. You got to be careful though when you have a kaleidoscope problem, because these two will be so nice it'll count as like one, and they're really two. So you have to look at something that's like a thumb sticking out, like something like this that sticks out here. because if you look toward the center and see beautiful symmetry, you can easily be fooled. So be careful when you count these. See, there's not three things here. There's really six. So just be on the lookout for that. Definition of polarization, of course, that's important. And the polarizer, that's good to know also, that the polarizer lets through one type. See, here's mixed polarization. Then half the light gets through, 50% here, and then if they're crisscrossed, then 0% gets through. In this case, you start out with 100%, you get 50% here, and then since they're crisscrossed, you get 0. If this one were aligned up, then that would go through 100% here, but then if you call this 100, then this is 50, then 50 would go through if these two were aligned the same way. And there's some pictures of applications. I think this pretty much does it. Malice's law, this is a cute law, that when you have the two polarizers, if the angle between the two of them should be theta, that's the axis of each one, then you take the cosine of that and square it. That tells you what gets through. So if they're lined up, then if you have polarized light coming in and they're lined up, then this is 0 and all of it goes through. But be careful when you start off. Usually with these cases, you start off with light from the sun. You start off with some mixed polarized state. So in that case, if you have one polarizer, half goes through. But now when the light is polarized, for the next one, that's when you use the Malice's law. That's when this law would kick in, this one there, because this is assuming the light is polarized coming in. Circular polarization will not be on the exam. All right, I think that we need to, and by refringence here, let's see if there's anything. Optical activity. No, I think we're finished with this chapter here. Yeah, I think we're good. We're good. All right, so let's go back here and find Rayleigh Scattering, Lure Rayleigh. And let's see what we have here. Just got to make this a little bit bigger. Yeah, like that, so we can see easier. Okay, we can skip over all this genealogy. Yeah, this is electricity magnetism. You're going to be tested on this in other courses, so you can skip over this. Although it's nice to know this formula. And it's nice to know this formula. N is C over V. And you want to know, this kind of a formula here. These two, the velocity. So that these three are good, but then all this up here you don't need to worry about. All this stuff you can skip. Definitely skip. And here, yeah, I think the main thing that you want to know from this is that to get electromagnetic radiation, you have to have acceleration. Because that was the point that we did earlier, that if you look at, so I wouldn't worry about this here. I'm thinking, yeah, this looks like too much other modern physics. Another course will do that for you. So let's go down to. Yeah, the resonance thing is covered mainly in your mechanics course, so I feel you'll be tested on that in another course. So here, I mean, this is good that we touch base with this stuff because the physics is related, but for the exam, I'm not seeing anything hitting me. Well, you want to know the general idea that in the greenhouse effect, the visible light gets through, but then the infrared, when like the upholstery in a car gets heated up or the ground gets heated up, the infrared can't get through. So you want to know that conceptually, like GRE type question. This diagram is similar. But then all this, you can kind of, this is relativity. So you won't, of course, that was just mentioned in passing. All this stuff can be skipped. Yeah, this is more of a derivation. So we're good. The main thing here is that you have to have acceleration. You might recall doing acceleration, but I wouldn't worry about any of this stuff. All right. Here, if these are flat, you generally want to know that the dispersion does drift up when you get short wavelength. That's the conceptual idea, GRE type question. You're pretty much flat here, a little bit of dispersion in the visible. Here's your visible, less dispersion in the infrared, and then things go wild in the ultraviolet where you're going to have the resonance. So it's good to know that without the detail of the mathematics. And then we can skip over all this stuff. And the sky is blue. This was meant to stretch your imagination and challenge you, but you wouldn't be given this on an exam. All right. Main thing here is that you are accelerating. That this is going back and forth. Harmonic oscillator, you're changing your velocity. You're going to go fast and then stop, turn around. So the acceleration gives electromagnetic radiation. So whenever you have acceleration and you got electromagnetic radiation, that's the main thing there. Okay, so and with the sky is blue, you should know blue scatters more. Of course, we already know that for the sky being blue, and it's nice to know the 1 over lambda to the fourth rule, since that's like a GRE type thing to kind of know that it's a famous power law, but you don't need to know the derivation that we work through. Right, that would take too much time. Okay, we go to Laplacian, and let's go ahead and make that a little bigger. So here, let's see. Yeah, it's nice to know the definition of the del operator, and the Laplacian, you just do del dot del like with your unit vectors and get this. That's good to know that definition. Here, then our wave equation, which we did earlier, that becomes part of the wave equation, like the one side of the wave equation. So what about this stuff? Well, this is a nice review of things that are in lots of physics courses. I mean, this is good stuff. This is your coordinate system. So you want to know your way around here, just in general. It happens in many courses, and your calculus courses and physics courses. So you do want to understand this pretty well. This we can skip, the Poisson equations. And curvilinear coordinates, we can skip the derivation. Yeah, this was all as background information to help you understand where Laplacian comes from, but we're not going to worry about curvilinear coordinates on the exam, and not need to worry about that either, or that. The main thing is here we're going to give you the Laplacian, or these things in the different coordinate systems. We'll give them to you. We don't expect you to memorize them. So this was more of a chapter to help give a foundation to these things, but they would be supplied. So you really don't need to worry about most of this chapter. You can kind of not worry about it. All right. You do want to know how to use that del operator if you took a gradient, for example. So you'd be able to use it, and we would give you the del. You'd only have to memorize the Cartesian one, because the Cartesian one is the one that's very, very simple to remember, and that's this one here. So once you have this memorized, you can do a gradient if we put a function there, or you could do a del dot, a divergence. So you want to know how to do that in Cartesian coordinates, definitely. Okay, then we go to Fourier. Now, Fourier optics has the series, and I decided that you didn't have to memorize this. I'll go ahead and give you this. So if we have one on the exam, you'll have your equations. Let's go ahead and blow that up a little bit more so we can see these here. You'll be given these equations, and you want to know how to use them. So this is good stuff. You definitely want to know how to use the things to get results. So we're really not concerned about this first part of the chapter. This was deriving the equation, so you can kind of skip over this. The main thing is the example, like this one here. Like you would be given, if anything, you'd be given an example like this, and then you're going to do one of these. So you can skip to get to this point here and know that this is an odd function here, this even function, so you can immediately, with something like this as an odd function, that you can have the zeros for all the even, the one a naught and am. So you want to know that trick, to be able to identify which ones are zero right off the bat, and then you want to know how to do one of these problems. So here's where you put your focus, down in there. The other has Fourier Transform. So you wouldn't have to know all this stuff. This is the derivation. What you would have to know is how to use it. So here you want this last part of each half of the chapter, and that would be here, exactly. So in other words, to be able to do one of these. So can you then, do one of the transforms? So that's the main thing. So it's the applications. So just skip over the derivations, go right to the applications and on that chapter. Then we go to Fraunhofer Diffraction, S. And for Fraunhofer Diffraction, what we're going to do here, now we would be giving you anything we would give you this if it were spherical course. We'd give you this, and then if you had to apply to a function, you would need to know how to do that. So it's not a bad idea to read through this. That if we gave you something like this and gave you the Laplacian in those coordinates, like the spherical coordinates, then you'd be able to work your way through. Okay, so let's say you should look at that. It's nice to know the Huygens Fresnel principle, that each point on a crest or a wave front becomes its new wavelet, and then that gets you the evolution into the future. So I call those the baby waves. All right, so Fraunhofer. Now for Fraunhofer diffraction, you would not have to set up something like this. What would be a better example for this? Well, you would want to know how to calculate your radians. We already talked about that. Take the modulus squared. All right. Whenever you have an I, it becomes then a minus I. See, like in there. So, here. Okay, so here's what you got. So this is the diffraction formula. So this is important to know how to use this. In other words, to know how to find, like, where did the minimum occur? Where did the minima occur? Like when the sine squared goes to 0. Maximum is a little tricky because this beta is going to mess you up there. But you would be guided, like, see, this maximum here is pretty much between the two minimum. Not exactly, because that beta in the denominator is going to mess you up. But you would, if you were to take that in the middle, you'd be able to work out a problem like that. That would be good. So to know how to use this, find the minima, and if you take the maximum to be like in the average between the two of the betas, you see two of the cases, like here's a case for beta, is going to get you a 0, and here's another one 0. And you take, say, the average, that you'd be able to play around with using these to, like, find things. And then also know that, like, the distance, like here, x going up like that, is related to the sine of the angle. Now, technically, the tangent of the angle is x over L, but when the angle is small, the tangent and the sine are the same. So you should know that the sine of the angle is x over L, the way we look at these for small angles, and then know how to use this to, like, you could find your x given your L, and find angles, and, like, for the minimum, no problem for the minimum. For the maximum, if you were given one of those, you would be told to take the average, do the one in between, because we wouldn't want you taking a derivative and set equal to 0 with all this mess in the denominator. That's going to be a little too complicated for an exam. All right, so it's talking about the minimum here, and it's talking about the maximum and some transcendental equation. See, we're going to stay away from that, but we might tell you, say on an exam, that just take this point to be like along, like here, like, and make it 3/2 pi. In other words, that would be like, just telling you, like, it's right between the two. See the 0 ones here, pi and 2 pi, that's when the sine of pi is going to be 0. The sine of 2 pi is 0. And if we told you to take the average and use this value, you'd be able to do that. We would not expect you to mess with transcendental equations. So if we give you this, you might want to work a couple out where you just slide this baby, pretend it's 3 halves pi, like it's right there, and then like work it out. See, this would be like 5 halves pi, and this would be 7 halves pi. Look, they're very, very close. Okay, so that looks good, and this is transcendental stuff. Yeah, we wouldn't be doing the transcendental stuff. And here's the similar idea that this is your pi, 3.14 or whatever, and this is then 2 pi, and that the one in the middle is not exactly in the center, like not exactly 3 halves pi. But if you make that approximation, then you can do it, and do it quickly. Here, we might, let's see, let you do one of these integrals. This conceptually, you did one of these for homework, so I have to just evaluate how long it's going to take. Because see, this already looks too long, but maybe I could ask you to do part of it. Give you part and say go from step A to step B. Irradiance, as I said earlier, very, very important. Okay, and there we go. Oh, this is for the two slits. So yeah, you want to understand this and how the interplay between the two. And this diagram is very nice. It shows you the faint one back here is the cosine squared term factor, and then this dotted one is your sine squared beta over beta squared, and then the solid red one is like the answer. And so you can see that this is very close to being between like these two zeros. You see, it's almost, but it's a little bit to the left, because see, that's the middle part right there, but it's very, very close. So, this is a beautiful diagram. Definitely study this well. This is good. It pulls it all together. Gives you the interference function factor. That's the cosine squared alpha. Gives you the diffraction one. That's the sine squared beta over beta squared. And it gives you the together, like when you multiply them. And you can see that that peak is a little bit shifted to the left due to, we were talking about that transcendental equation. And notice that some of these orders get missing. So they knock out some of the orders are missing, third order there. And then the single slit, the single slit formula, we already did that, the double slit, and it's important to be able to use those and to get your way around those. And remember the screen, the x along the screen divided by the distance of the screen, which was L in one of those diagrams, is your sine of theta. You want to know that also. So the fraction 2, this is more of the same thing. So we might give you something in the have you do one of the steps here, because this conceptually very easy set up. You did this for homework, so we just have to gauge how much time it would take and maybe do a portion of it. So you do want to know that, and you had one of these to do for homework. Yeah, this is all good stuff to study. Definitely study this. All these tricks are good. It's good to go through this. Even though that's going to be too long for the exam, we could put part of it. Construct the part of it. And know your L'Hopital's rule, very important. And normalization, why that n is there. So this is very good to know this. And then if the big N is 2, the formula reduces to like what you had earlier. It's like if you have like one slit, then this kid goes away. You just have this. It was 2 slits. So it's nice to see how the 2 slit problem, the 1 slit, this is very good stuff. I would definitely look at this very carefully. This is good. This is good. This is good. All this stuff is good. And this is a nice picture to look at. So definitely go over this part of the chapter. Just very good stuff. The rectangular aperture gets way, way too involved. So I would say here, the homework problems are a guide where we use this for the homework. We did a homework problem using this. That's the more important thing there, because that gets too much. And no way. Circular, no way. This has the Bessel functions. No, that's not going to be on the exam. You might want to know this, though. This is a cool relationship. Very, very impressive relationship. that has the Rayleigh Criterion, and it has to do with, going to that darkness and that the first minimum with the airy, this function, the airy disk. So this is important in resolution. So I would memorize this. This is good. This could show up on GREs all the time. That's very, very good stuff. This you can skip over, and that's just a picture. All right, so let's go here. That was T. One more. We got one more to go. We got one more, and that's the Fresnel. So for the Fresnel, let's see what we got. This is kind of nice to know. This is your obliquity factor. It basically gets you a 1 if you're going forward, gets you 0 if you go back, and if you're at 90, it gets you a half. It's kind of nice to know that factor is important for the wavelets. Here are the baby waves, the Huygens-Fresnel principle. This general form of e to the I kr over r is not bad to kind of know that's the general way to handle the baby wavelets. So that's nice. You can see where this is coming from here. You got a baby wave. You got the main wave here with the primes getting you to this point, and then you hit it again using the baby wave concept and get that. So it's kind of nice to know that setup. That's a very good setup. That's your basic equation. See, that's your fundamental equation. Now, when we start doing all kinds of approximations and things to work with it, I would say you don't need to worry about that. That's too much detail. So here, I think it gets into complexities that would not be on the exam. Now here, but you do want to know the general idea that your Fresnel zone, the next one's going to begin here with the plus the lambda over 2. When you look at this distance, you're going to have an extra lambda over 2, and then you're going to have then 2 lambda over 2 and 3 lambda over 2. So you kind of want to know that general rule. And see, there's your general formula. And here, these derivations, I think, you should know how to do a Taylor series expansion, but we're not going to put this on the exam. This is derivation. But we might isolate like one of these, like if you had this and you said that one of the parameters is very large compared to the other, what would it reduce to? So that principle is important, and that's like a subset of what's going on. But all this stuff you can skip over. You don't need to memorize that, the Fresnel zone thing. No. So here, it's plugging in numbers. And for the unobstructed wave, this is not bad to kind of have a bearing on that. If you are looking at the unobstructed wave and adding up the Fresnel zones, you're going E1 plus E2 plus E3 plus E4, and then you get 1/2 of the first one. See, the first one got you up to the top, that's 1/2. So this conceptually is very nice to know that if you block out all the zones, you get the first one, see? And then if you blocked out all of them but the first 2, they would tend to cancel, see? So that's kind of nice to know this general kind of an argument and to understand conceptually what's going on here without the math, just kind of like the idea. Okay, and this too, this is very conceptual stuff. This is good to read through this, the circular obstacle. There's very little math here, so I would definitely look at that. And okay, that's just talking about Young. Can skip over that and the spot. So we're basically finished. I would know about the spot. That's kind of neat. Know about that. And this brings us to the close of the chapters. I think I wanted to look briefly at the homework to get you an idea of the homework. So let's go to the homework solutions, starting with O. All right, let's look at this, because this may even give us a better idea of what could be on the exam. So here, this kind of a problem, I don't think this one's as important. I would skip over this one. The quarter plate design, it's not bad to understand your way around phase, like your KX kind of thing, your K times D. So I would look this one over here. It has some nice basic formulas for you. So that's kind of nice to look at. And let's see here. Yeah, the two cases. The birefringence problem, this one would be too hard for an exam. Take too long. So we're not going to be doing that. Well, wait too long. You're not going to be able to do that on an exam. No, no, no. We can skip over that. No, answer is no for that one. Okay, so let's go to homework P and see what we got. This one was a derivation we led you through, so you can skip it. We're not going to be doing this. Yeah, no, no way, no way, no, no, no. This was leading you through a derivation, so you can skip over that. All right, let's skip over that one, and then we go to Q. This one I'm going to say skip over because you get tested on this in E&M course. So you're going to get tested on this thoroughly somewhere else. So we're skipping this. No, skipping that. As I said earlier, you should know how to do in general. If I gave you a general vector, but the application here for the E&M would not be, no, this would not be on the exam. This is, we wanted to do some of this stuff because it overlaps with optics, but the main center of gravity of this stuff is in a different course. This is an electromagnetic theory, so you'll be tested on that elsewhere. So no for that. Okay, so then we come to R. Now for R, yes, this is this is good. This is an example. We said earlier in the chapter, you want to know how to do those. So definitely know this. And look how short that is. That wasn't very long at all. That could be on the exam. Ideal kind of question for the exam. Fourier Transform, yes. Come back here. If we had this as a straight line that was flat, that would be a snap. So I'd have to think about this. I'd have to give you integrals. I'd have to help you. So this one is a bit much, but definitely know the straight line one and know your way around that. But that one there, because of the integrations, got a little wild. You would have to get help or maybe do part of it. It'd be part of an exam question. Okay, so then we go to S. Yes, this is very good. You can to be able to work your way around this. Look how short. See, this stuff is. This is definitely good. This one here, the triple slit. Conceptually know how to set it up, but the entire question would not be on the exam. It takes too long. But we could ask part of it. We could say start from point A and go from point B. So this is like a straightforward kind of a problem. Just takes too long to write all the stuff out. And there's your formula. But know the process for that. And now we do T. This is a very good problem. This is a very good problem that pulls everything together. Definitely. Good stuff. You definitely want to know how to do this problem. And this is great stuff. Great problems for exam. Master those. And the binary star one, this is good. See, look how short. Very short and sweet. So this is very important homework assignment to work with and to understand. Okay, if we go to the last one, U. Here, this is a derivation. No, I wouldn't worry about this. This was a derivation. And this one here was a derivation also, and that does take a little too long. So I would say you can skip over this. I think that you can concentrate on the other stuff. Yeah. Okay, well that's the guide. Remember, no guide is perfect, but this guide I think will help you a lot and help direct you. to what to study for on the exam there. So good luck, and if you have any questions, just email me as usual, and I'll write back. And anything's not clear about the review, what we talked about, just let me know. So there'll be, let's see, format-wise, it looks like we're talking about 10 multiple choice, 30 points total for that, and then a 20-point problem, a 20-point problem, a 20-point problem, and a 10-point problem. And all the problems, each of them some of them will be like a part of a major problem, like you're not asked to do everything, so it would take too long, but maybe do something, a part of something. And in other cases, if you do everything, they'll be fairly short in terms of your analysis and plugging in and getting things. And this exam does allow for a calculator, so you can have your calculator out, and it'll be, of course, close everything else and on your honor. Okay, good luck.